my initial response to John's invitation was a kind of misunderstanding. I thought maybe I'm just a participant to join the group so I can listen and to learn. But I was not expecting actually to give 7 slides and also to explain my ideas about a quantum entanglement or origin of life or universe. So that's kind of a force on me, but I will try to do my best. But I understand that within 10, 20 minutes, I probably can do nothing other than just a very simple overview. I'm just picking this angle, this perspective to talk about the evolution of the cosmos. So in the hope that to establish some kind of a framework so we can discuss the different systems and the different evolution process inside, right? So let me begin with the first slides. I changed my slides a little bit, but I didn't got a chance to.
Have you shared it? Have you shared your slide yet?
My question is, my slides is on my desktop while I'm using the Zoom. The Zoom on my cell phone. So I think these two systems are not connected. I don't know. I can share, but I think it is basically the same. It's just a slight difference. So let's live with that. Okay.
Okay.
The first slide, I want to talk about the evolution of different scale, because the systems they're evolving not at the same scale. They always increase the complexity and the structures of change upon certain degree. That we're not talking about the same degree system anymore. For example, the first material generated was like protons and the photons, and then you have the nuclear, then you have the atom, and you have molecule, and also there's a life proteins, and so the system is actually changing all the time in complexity and the scale. So I understand John has a very ambitious goal to establish a whole holistic system to combine physics, chemistry, and the physiology. I really admire that ambition. Actually, if I can be of any help, that would be great, John. There is some kind of continuum, though, from the very beginning, this singularity to our human society today. Actually, there was a new book published, I think probably 2 years ago, by David Christian. He wrote a book called Maps of Time. That's like a macro history narrative trying to explain from the very, very beginning singularity to our society today. I think that's probably a book worth reading. I haven't finished reading that, but I think that's a great book. Actually, at least a great effort. Okay, so when we're talking about singularity, I don't know what we should talk about. Are we talking about a universe singularity or our human life? From reading John's articles, I'm not totally clear which one John is referring to. If it's a physical singularity, I think there's so many physics or theories. They've been talking a lot about singularity. Simply put, singularity is just an area at the very, very beginning that is beyond the explanation of general relativity. Right? Is that the mathematical laws no longer apply in that point. So there's like a super, like a intensity in energy, and infinitely small point. So nobody really knows what a singularity is now. Of course, there are some theories. I'll refer to that later. Then the singularity state is a quantum fluctuation state. It's not nothing. It's not a vacuum as we understand in the daily life, daily terms. Okay, so I will talk about a little bit about quantum fluctuations later too. And when we look at atoms, the size of atoms from the smallest to the biggest is probably like from 30 to 300 ppm, right? like a helium is the smallest, and you have a cell system as the biggest atom. Then you look at a molecule that's about from like H2, 0.72 nanometer to 10 nanometer, like PG5, this artificial molecules created by humans. Then you have a unicell. There's also another scale. There's a 1.5 to 10 mu m, or multi-cell from 100 to 100, 10 to 100 mu m. So if you look at the ratio between unicell versus cell, there are million times difference in size. So I really doubt if we can have like a unified theory to explain all various, a principle, a theory to describe all systems. So probably we have to deal with each system separately. Like there's a hierarchy of systems, right? From atom, molecules, protein, cell, tissue, organ, human societies, for example. Then we need different terms, different concepts, and different theories to describe different systems. Like at the beginning, we probably want to use quantum mechanics to explain the very, very beginning of the universe, and also it's all these subatomic matters. And then we use special and general relativity also to explain the gravity and the space-time relationship. And then we have a Newtonic classical theory to explain our human size world. And then there are other studies like biology. You study cell by cytology and biology and physiology. So can expect use a unified theory. That's just my thinking. I don't know if I'm correct. Then the second slide, this is just very visual explanation about the different sizes from atom to human beings. So you can, at the very beginning, we have like an atom. Atom is not a beginning, though. There's a lot of other particles, like quarks, and photons, protons, before atoms. And then gradually you have the very simple form of life, lipids and organic materials, I put that way. And you have then a protein and the virus, the bacteria, and all the way, right? So you can see so different in size. So each one should be probably treated differently by different theory. Okay, the next slides I want about actually it's a further explanation on my previous point. Okay, so I made a table. I don't know if let me see. Okay. At the beginning, you only have or probably I can. Let's come to the next slide, Jason. I'm sorry. Let's move to the next slide. I want to, just skip this one. Yeah. This one, I changed the table a little bit. Okay. From the beginning of the universe, before that was singularity. Okay. Let's say the singularity ends on Planck time or epoch. Yeah, as a 10 to the order of negative 43. Then you have extremely high temperature. Right? It's a 10 to the order of 32. So in this period, there is no difference. Okay, so all the universe is even. Okay, so there's no. It's extremely even. The fundamental forces, four fundamental forces are united. Okay, so you cannot tell if that's a weak nuclear force or a strong nuclear force or electromagnetic force or gravity. Gravity was created afterwards. Yeah, in the GOT period, then gravity was separate from the other forces. And then you have the inflation period, and then all the strong nuclear forces were separate too. Then you look down the table. Then you find a quark was created at this certain period of time, right? It's not like from beginning you have a quark. In the beginning you don't have a quark. at the beginning you don't even have a strong nuclear force, because there was no nuclear. You cannot, you don't even have gravity because there's nothing to gratify to, right? So all these forces or matters all created during the process with the creation of the universe. Okay, I just pick another one. For example, nuclear was created between 10 seconds after the Big Bang to 1,000 seconds. That's the nuclear. The period nuclear was formed, was generated and formed. Then let's move down to recombination period. That's the period when the temperature drops to 4,000 Kelvin, and electrons and the atomic nuclear first became a bond to form neutral atoms, right? Then you have the dark age. Okay, the dark age, you cannot see through dark age. Okay, so all the known universe stops there. So that's why you have this CBM, right? This is the background wave, universe, cosmic wave. That's where the farthest you can observe in the universe. Yeah. Beyond that is just theories, mathematical calculation. Then the story afterwards is simple. You know, when the galaxy was created all the way. So in the whole process takes about 13.1 billion years. Okay, in the process, temperature dropped from 10 to the order of 32 Kelvin to 2.7 Kelvin. Okay, that's our background, the temperature, the universe background, the temperature, and then particles at a lower temperature lost their freedom to move. That's why they got trapped and got combined to form mass. Now you have atoms, because at an extremely high temperature, all these particles like photons and neutrons, they are just free moving. They will not bind, they will not combine, they will not form material, mass. Okay, this is only when the temperature dropped to a certain point, they lost their energy, they lost their momentum. So that's why they have to be trapped, yeah, to form a mass. Okay. So this, and also this is a process to increase complexity. The complexity increased. At the beginning, there was no complexity. Everything was unified. It was even. Then, with the drop of temperature, with the time goes by, then you have complex increase. So everything is in the universe is evolutionary created, including elemental particles, including all fundamental forces, including all physical laws, including, of course, human, right? So everything was not until was created at a certain point of time, right? So the universe itself, in my view, is a changing concept. There was no constant universe. Everything was changing and forming. Even time was created. Even space was created, right? Let me probably say another angle that so the initial even unified state of the universe is by super high energy and temperature. Okay, then you have this second thermodynamic law kick in. You have a negative because in the process of spreading energy and the temperature drop locally, you have a negative entropy formed. Okay, because it doesn't always follow the second thermodynamic law. In locally, there could be a negative entropy form, and if this negative entropy is captured by a membrane for any boundary to form a system, so and the system can circulate and can be filled by like John mentioned, the chemiomosis, or so this homeostasis will be maintained within this membrane with this isolated environment, small environment. and to be separated from the general big environment. That's how complexity increased and how life was eventually created. Right, that's my point. Okay. Let's see if I can probably go to the, I will skip a couple of slides. Actually, I made a new slide, which is not on Jason's, was not provided to Jason. I'm sorry for that. But I do agree with Jono. The whole process, the creation of the universe and the evolution is a quantum phenomenon from the beginning to the end and all the way in between. The whole process is a quantum phenomenon. Why? Okay, I have already explained something about the beginning, and later I will talk about some process, why this is also quantum. And I was talking about singularity. I said I will refer to this point again. So now I want to say probably a few words about quantum fluctuation. So, or you call it a vacuum fluctuation. Yeah, it's not a nothingness. There was something. Yeah, but it's called there was some random fluctuation before Big Bang. Right? In the value of fields which represent the elementary particles, such as, for example, electric or magnetic fields, which represent electromagnetic force carried by photons, or the W or Z fields with the weak force, or the gluton fields which carry the strong force. Or this vacuum fluctuation appear as a virtual particle. Why is it called virtual? Because they were created and then annihilated, which then disappeared. Right? Are always created in a particle anti-particle pairs. Okay, they were busy. The world before Big Bang was busy. Yeah, this is like a very active creation and annihilation all the time. Yeah. These pair of particles, because they were created spontaneously without a source of energy, zero energy, but they could be created because the vacuum and the virtual particles are said to violate the conservation of energy, but it doesn't really. According to the Heisenberg uncertainty principle, it says uncertainty energy time can be expressed by a formula, which I will not read out the formula. This means pairs of virtual particles with energy delta, the actual energy created delta E, and the time for this E delta T are continuously created and annihilated in empty space, but they're so fast they cannot be observed by our human beings. It cannot even explained by the Heisenberg formula. Okay, so there's a lot of experience already, like the Casimir effect, the Lamb shift in hydrogen, all these things can confirm that all this quantum effect all are actually affecting our human-sized world. Yeah, actually, this last year, there was a very interesting experiment conducted. I forgot it. Maybe MIT. I think the MIT group they conducted a very interesting experiment. So to measure the quantum vacuum fluctuation on the motion of macroscopic and human scale objects. So that's a very interesting experiment. Yeah. You can Google that. It's MIT legal experiment to the quantum vacuum fluctuations on the macroscopic human-sized object. So because of the common misconception is quantum physics only affects microscopic world. It doesn't affect our macroscopic human world. That's not true. Okay, so everything can be traced down to quantum fluctuations, which obey the quantum physical laws. Okay, So that's the beginning, the origin, and talking about the process. Why the process is also a quantum phenomenon. Okay? I want to talk about the Feynman historical path integral theory. I don't know if you guys are familiar with this, but this is actually another expression about quantum mechanics. Yeah, it's the sum over all possibilities. Okay, let's say this is a picture from point A to point B. Then at the time TA and 2 time TB, it's not just one path. There are many paths. There's so many paths. There's a context of paths. Okay, so the TB, why TB exists, because the state at the TA will travel through different paths and will merge, will converge at the point B. So if we do the integral calculation, then you can come up with a result, a state of location B. Right? So Feynman said that the history not only has one history, but it has multiple possible histories. Okay, and talk about human beings, our human structure and the function is but only one possibility among millions of paths. So be humble, gentlemen. We are just one in a million or billion possibilities. Okay, the diagrams below is actually a simple version of a double slit experiment, right? This is a famous double slit experiment to explain why a particle pass through a hole. Then it seems like a simultaneous pass two holes at the same time. That's not true. Actually, you cannot understand this double slit experiment from the particle point of view. It's not a particle, because people say, oh, there's a duality. It's both a particle and a wave. In my view, it's all wave. A particle is just a sort of like a condensed wave. Right? If you have a extremely condensed wave, you view that wave as a particle, but fundamentally, in essence, it's still wave. So how can you, when you project a wave against a wall with two holes, of course the wave will pass two holes at the same time, right? So if you have this is a simplified picture though. You have another wall, you have another wall with a different number of holes. Then at B, the point B, this is it's a combined effect of all paths affecting that point. Okay? So human beings and the universe, especially. Okay, let me put that another way. Okay. I'm a little bit excited. People might have a deterministic way of thinking all the atoms and this periodical table is a definite result. John, I don't agree that is a definite result. That's particle creation and molecule creation, atom creation was also uncertainty. There's uncertainty. This is just one possibility. That could be formed in different ways. Okay, it just happened to be that all human beings are on this universe, on this pathway. You see all that periodic table, but in a different universe, you might see a different periodic table. You have different particles because there's a choice, the multiple choice. The particles can be formed this way, it can be formed the other way in other universe. Okay, so that's my point I want to make. Okay, so my final slide. I'm sorry, Jason.
No. I mean, be brave because we still have one more speaker.
Oh yeah, I will finish it quickly. Okay. Then comes to human. Okay. I like to study brain a lot. Brain actually the very element that exists already in the very simple unicell existed 3.8 to 4 billion years ago. Okay, actually, there's a French study, a French university. They made a study 4 years ago about a protist. Okay, they proved the protist is capable of learning. Okay, how can protists learn if there's no like stimulus and response and feedback? How can a protist learn? That's a very first form of your neuron system, your neural system. Then you come to like a 3.4 billion years ago, you have a bacteria. The bacteria has ion channels already. It has a membrane control the flow of ions. That's also a base for nervous system. Then you have like 2 billion. So you have the eukaryote capable of making electrical signals. Then fast move to 600 million years ago, you have sponges, you have like a jellyfish.
Your time is up.
Then you have a those things didn't have neurons, but it have homologs of many genes which play key roles in synaptic function, like a human being. Okay, the mechanism was already there. The very structure important for synaptic structure was already there 600 million years ago. Okay, and then you have a platform.
Okay. Time is up.
Yeah.
Our group has kind of a
preset. One second. 1 minute. Yeah, Jason. 1 minute. Okay. First move. Okay. To now, then evolve all the way to our human beings, and we have this new cortex of 6 layer structure. Right? Yeah. That's a phenomenon. So consciousness, in my view, okay, it's because John mentioned about consciousness. Consciousness is, well, if you broadly define, maybe you can trace back to the atom level, but I think it's more for common people is more above cell level, and and it has a lot to do with language and a lot with the Broca and the Wernicke system with your brain. And I was in the process trying to translate the book written by John Edelman, the Nobel Prize laureate, and he understands consciousness as a re-entry based on neuronal substrates in the network. Okay, let me finish my presentation now.
Oh, thank you.